This video covers the photoelectric effect. Now here we're talking about the work function phi. This is the energy needed by an electron in the ground state, which is the ring or energy level closest to the atom, to the protons or the nucleus, to reach the edge of the atom, which is the outermost energy level. In this case, it would require 10 electron volts in order for it to move from the ground level to the outermost energy level. You saw in the last video that if an electron absorbs more energy than is needed, in this case something greater than 10 electron volts, then it'll actually have so much energy that it will leave the atom. Once it leaves the atom, it's going to have a velocity, therefore a kinetic energy. So the amount of kinetic energy it's going to have is however much it took on minus however much it needed to get to the edge of the outermost level. The difference between those two is going to give you the amount of kinetic energy. We can calculate the kinetic energy if we know the energy absorbed minus the work function, or we can replace energy by this equation here, and this is Planck's equation, where h is Planck's constant. And we'll see more of this in class. F is frequency, and E is energy. So we can replace energy with this Planck's constant times frequency, again, still minus the work function. Or we can replace frequency with C over lambda, which comes from the equation C equals frequency times lambda. Again, we've seen this equation before. We're just substituting this in for frequency. And now we can substitute that in for energy. Now we said that these electrons that leave the atom are moving, and moving electrons together, several moving electrons, are going to produce a current. That means that this photoelectric effect is responsible for solar power. Solar cells are also photoelectric cells, or photocells. So light's going to come in, hit this photocell, and with enough energy, kick off some electrons. These electrons are going to be moving with a kinetic energy. And we know that atoms that give up electrons are now becoming positive. So if we connect that to a plate where electrons are gathering on one side and the plate is now becoming positive, well, you can see here that we essentially have a battery. Now here it's actually going to be important to understand that the photoelectric effect tracks the negative electron flow instead of the positive current like we've seen in circuits. Again, light's coming in, making the electrons pop off of this plate, right, this photocell, and then those electrons are going to travel through my circuit. Now we're going to place a variable power supply, meaning a generator that we can control, and an ammeter, again, which reads current, into the circuit. Now we have what's called a photoelectric effect experiment. So what happens is a variable power supply is positioned backwards, creating a clockwise current. And this is adjusted enough to where the ammeter reads 0. That means that the forward current from the photoelectric cells is going to be counteracted by the current produced by our generator. Again, when that happens, the voltage of the photocell is equal to the voltage of the power supply. So that means we can actually use a power supply to determine what's the potential across my photocell. This is called stopping potential because it stops the current. Once this happens, there's an interesting relationship between the stopping potential, measured in volts, and the kinetic energy, measured in electron volts. So let's say that you have a stopping potential of 6 volts. Well, if our potential energy equals kinetic energy, and our potential is 6, our charge is 1.6 times 10 to the negative 19. Again, remember this equation from electrostatics. Then we can multiply those two values together, and we get joules. Now, to convert from joules to electron volts, we have to divide 1 electron volt by 1.6 times 10 to the negative 19 joules. This gives us kinetic energy, and you notice that it's the same value as we have our potential. Now, this conversion factor from joules to electron volts was selected so that the voltage acting on the electrons could be converted into kinetic energy of the electrons without doing any math. So, if we were to look at a graph of this information, again, our kinetic energy is equal to our energy minus our work function. Then we can graph it like here, where kinetic energy is on the y-axis and frequency is on the x-axis. Now, this slope of this function is going to give me Planck's constant, h. That means that the y-intercept is our work function. And the x-intercept is actually called our threshold frequency. Now again, because of the conversion factor between kinetic energy and potential, we can actually just switch the units and everything would stay exactly the same. So again, if you look at this graph, anytime that we have negative kinetic energy, that means that we still have some potential energy, which means that we have not left the atom yet. So when we're graphing the photoelectric effect, we only want to graph the positives because that's when the electrons have escaped the atom. Also, this part is very important. The energy values are negative for electrons inside of that atom. This is why the x-intercept is known as a threshold frequency. It is a frequency required in order for us to have photoelectric effect. This photoelectric effect is actually evidence that light acts as a particle. If the energy of the photons increase, which means we got a higher frequency, then the energy of the emitted electrons actually increased as well, but the number ejected did not change. So, if the number of photons striking the photocell increases, then the number of ejected electrons also increased, but the energy of each electron was not affected. If the photons do not have enough energy, then no matter how many photons strike the photocell, still no electrons are emitted.